Welcome back to the next session. In the previous session, we were discussing about this short circuit power dissipation, and we saw how this short circuit power dissipation can affect uh, the performances, like how it comes, and the different parameters we talk about, like how we can reduce this short circuit power dissipation uh, with the help of this TSC or TS, or simply rise time or the fall time, threshold voltage, and other parameters. So these all are the parameters that decides like how we can reduce the short circuit power dissipation. One very important thing that we have to consider, like we have the load capacitance here. If you see the previous slide here, we have the load capacitance, and the size of this load capacitance play a major role, especially if I want to reduce the short circuit power dissipation. Okay, so let us try to see how this short circuit, like the effect of the CL uh, can change the short circuit power dissipation. Okay, so uh, suppose, let us consider the first case. If the load capacitance is very large, okay, so if the load capacitance is very large, so let us assume I have the input something like this, and input I am changing from 0 to 1. Okay, in that case, what will happen? If the load capacitance is very large, so the output fall time is significantly larger than the input rise time. Because see, if the load capacitance is very large, what it means, it will take more time to charge. Okay, and if it will take more time to charge, what it means, the charging time constant, like this output voltage initially, let us assume it was 0, so it will take more time to charge from 0 to 1, or discharge from 0 to 1. Okay, something like this. The waveform will be something like this. Initially the input was 0, so the output will be 1. But if the rise time is changing, like something like that, in that case, because the capacitor is large enough, so it will take more time to charge it. Okay, in this case, what will happen, the output fall time is significantly larger than the input rise time. Under this constraint, what will happen, the input moves through the transition region well before the output start to charge. Okay, so because the rise time is very less, so it will change from 0 to 1 suddenly, but the output will start charging just after this. Maybe we will not, the capacitor will not sufficiently charge, even though if the logic is changed from 0 to 1. Okay, so what will happen in this case, we will see, like, because the input was 0, and this was also we were not getting any of the capacitor that was like the short circuited, because if the input is changing from 0 to 1, uh, in this case, the output capacitor that or the output node voltage will look like this one. Okay, and if it will look like this one, so now let us try to map both the characteristics. Input is something like this, and the output is like very slow, something like this. Okay, in this case, might be the point at which it is crossing, it is above VDD minus VTH. Okay, so if it is above VDD minus VTS, the short circuit current or the short circuit power dissipation will be 0. So there will be no short circuit current that will flow through the circuit. And if there is no short circuit current, what it means, by increasing the size of CL, we can reduce the short circuit current that is flowing through the transistor, or flowing through this circuit. Okay, so the CL, by increasing the CL, we can reduce this ISC. So the ISC that is flowing through, yeah, so the waveform will look like this one. So the ISC that is flowing through this one, that will be reduced to 0. Okay, so the one advantage we are getting after increasing this CL is, like, we can reduce this short circuit power dissipation. Okay, but on the other side, because it is taking more time to charge, similarly it will take more time to discharge, so charging and discharging time constant is very high, so the delay will increase. Okay, so see, there is a trade-off between delay and the power. if I have to reduce the sudden short circuit power dissipation, in that case I have to increase the CL, and by that way you can reduce this ISC. But if but at the same time the delay will be higher. Okay. And similarly in the second case, let us try to consider the second case. If the CL is very small, sorry, it's not large. If the CL is very small, in that case what will happen, the input will change something like this, but output change will be faster, as early than this one. If it is early than this one, what will happen, there is a probability that the short circuit power dissipation, like, they can match for longer time period. So suppose it is something like this, something like this. So the probability of this short circuit will be more as compared to the first case. And if it is like that, then the short circuit current will not be zero, it will be maximum. So if the CL is very small, then short circuit current will be maximum. Then I max we can observe if the CL is very less. Okay, so this is the important thing, and that need to be considered, especially if I'm talking about the effect of load capacitance on the short circuit power dissipation. Okay, let us try to combine, let us try to relate three different cases. Suppose I have three cases, and on which I am getting like the spike of this short circuit one, something like this. Let us assume I am observing this spike for short circuit current. Okay, so this kind of spike I can get. Yeah, let me try to draw three different curves so that you will be able to understand. Okay, one curve is this one, second curve is this one, and let us see the third curve is something like this one. So can anyone tell which of the graph is having a larger load capacitance and the smaller load capacitance?
Sir, the green one has largest and red one has smallest capacitor.
Perfect. Okay, so the green one has the largest load capacitance, so CL for this one, CL is maximum. For this, CL is minimum, and for this, sorry, moderate. And for this case, CL is minimum. Okay, so this is the relation that we should consider. Now the important thing is, like in the previous slide we saw, like the ISC or the PSC, that depends on the rise time and the fall time. Okay, that also depends on the process parameter, that is the mu cx w by l sizing, that depends on the sizing as well. That also depends on the threshold voltage of the device. Okay, so if we go back to the previous slide, in that case we can see like what are those parameters. So like PSC, that depends on this tau. This tau is nothing but the rise time and the fall time constant. So if I will reduce this tau, then the PSC can be reduced. Okay, if I am increasing or decreasing this operating frequency or the input frequency, in that case this PSC can also be changed. The threshold voltage play a major role on the short circuit power dissipation as well, and also the supply voltage whatever we have used, that also play a major role in this case. Okay, so if VDD is yeah, so these are all are the factors that decides like K, tau, F, VDD, and VTH. So these five parameters that can decide what is the power dissipation or the short circuit power dissipation that is flowing through the circuit. Okay, so this is the important term that we have to consider. Okay, so let us try to see how we can manage like the parameter that decides uh, to minimize PSC. The first parameter is the K, process parameter K. K is nothing but here, if we see the mu and CuAx, that cannot be changed. Mu is the mobility, CuAx is the oxide capacitance. If I have fixed the oxide, then the CuAx cannot be changed, but the W by L can be changed. So by changing the W by L, we can uh, change this PSC. The second parameter could be like the rise time and the fall time, tau. Okay, rise time and the fall time can also play a major role on this one. So if I am reducing the rise time and the fall time, in that case short circuit power dissipation can be changed. The third parameter, that could be like the operating frequency or the input frequency, whatever we have used. The fourth parameter could be like the threshold voltage of the device. Okay, and the fifth parameter could be like the VDD, whatever we have used. Okay, so these are some of the parameters that decides the short circuit power dissipation through the circuits. Okay, so this is all about the impact of CL on the short circuit power dissipation. Now let us talk about the different kind of uh, power dissipation, and that kind of power dissipation we call it the static power dissipation. So let us talk about what this static power dissipation is. Okay, static power dissipation is nothing but this is a steady state power dissipation. Okay, so if like the logic is fixed, as I already told you, if the logic is fixed, in this case there may be some current flow through the circuit, and that can create the problem. Okay, so suppose I have the CMOS circuit, something like this, and let us consider the input is changing from 0 to 1. Okay, but the static power dissipation that can happen only if the input logic is not changing. Either the input is at logic 0 or it is at logic 1, and if this is the case, in this case the static power dissipation will come. Or okay, so if this is the case, in that case let us assume the input is at logic 0. If input is at logic 0, in that case this transistor is in the on state, like the pull up network is in the on state, and the pull down network is in the off state. If this is in the off state, then what will happen? It will if this is the case, there will be two parameters. One will be like, see here, because the input is 0, so output is logic 1. Okay, output is logic 1, so there will be one reverse bias diode junction that will be created between the body terminal and the drain terminal. There will be one reverse bias junction that will, that reverse bias junction or reverse bias current I will tell you in the next slide when I will talk about the leakage power dissipation. So please hold on that. But for now, just let us try to understand. We can have one reverse bias diode junction that will be created between the body terminal and the drain terminal, and because of that some reverse bias current will flow through this one. And also because the device, like the NMOS transistor, is in the off state, some sub-threshold current will also flow. What is this sub-threshold current? I will tell you in 1 minute only. Then in the next slide I will tell you what is the sub-threshold current. So the two components, the current component that can flow between the output node or this drain node and the ground one, because the body and the ground both are same, like the body terminal for the NMOS transistor is connected to the ground one, and the source terminal of this NMOS transistor is also connected to the ground one. So there is a two current component that will flow between the drain and the source, and the drain and body, and that is the one is the subthreshold current, which is represented in the red color, and the second one is the reverse bias diode junction that will be created between the drain and the body terminal. Okay, and because of that, because the NMOS transistor is always in is in the on state, but two current component we are observing at the pull down side, so we will slightly get a path between VDD and the ground that will flow, or the current will flow in this direction. So if this is the case, the power dissipation we can observe some static power dissipation. So basically static power dissipation means because of the secondary short channel effects and the reverse bias diode junction, subthreshold leakage currents, the other transistor is in the on state. Okay, and if this is in the on state, then one transistor is in on state, and the second there will be some current that will flow through the second transistor, so we'll get some path, and because of that there will be some power dissipation, and that power dissipation we call it the static power dissipation. Similarly, let us try to check the second case. Suppose I have an inverter something like this, and the input, let us assume the input is at logic 1. Okay, if the input is at logic 1, then what will happen? This NMOS transistor is in the on state. Okay, so this is always in the on state, but again, because the PMOS transistor is in off state, so that will create the reverse bias diode junction. So the pull-up network will create the reverse bias diode junction, and some current will flow in the reverse direction. Okay, so some current will flow through this one, like here the body terminal and the drain terminal, there will be a reverse bias diode will be formed between the body and the drain terminal of the PMOS transistor. Okay, and that current will flow, that we call it the reverse bias diode current. Okay, and the second current, that will be the subthreshold current, will also be there in the pull-up network as well, or the PMOS transistor as well. So in sum, we will get some path in the pull-up side, and because the NMOS transistor was in on state when the input was at logic 1, so we will get some path between VDD and the ground, and because we are getting some path, the power dissipation will be there. Okay, so this is what we call it the static power dissipation. So in summary, the static power dissipation is the power dissipation due to the reverse bias diode junction and the subthreshold leakage current. See, reverse bias diode junction and the subthreshold leakage current, these are the part of the short channel effects. Okay, these are the short channel effect, the part of short channel effect. So if the short channel effect is there in any of the devices, then the static power dissipation will definitely be there. So for the long channel devices, these short channel effects are less, so the static power dissipations are less for the long channel devices. But for the short channel devices, for the lower technology node, the static power dissipation becomes also one of the prime concern, especially in the VLSI circuit design. Okay, so this is all about the static power dissipation. And the static power dissipation is like whatever the current that is flowing in a particular state. When the input was 0, then there may be some current that will be flowing, and if I multiply with the VDD, then I will get the static power dissipation for logic 0. Similarly, if I have given the logic 1 at the input side, and then there will be some flow of current that we call it I static for logic 1, and then we can calculate the static power dissipation for logic 1, and after averaging both the things, we can get the actual static power dissipation for this one. So P static for logic or for the circuit, for any circuit, is nothing but the P static if the input is 0 plus P static if input is equal to 1, and then we have to just average it. Then we will get the total power or the total static power dissipation in the circuit. Okay? So this is the expression, or this is the justification for static power dissipation. Okay, so this is all about the static power dissipation. Now let us talk about one very important thing, or the important power dissipation, and that power dissipation is the leakage power dissipation. Before I discuss the leakage power dissipation, it is really very important to understand what are the different short channel effects that comes into the picture. Okay, and those are responsible to generate the secondary carry, or the currents that can flow in the devices. Okay, so let us try to see it. Suppose I have a device something like this. Okay, so suppose I have the first device something like this. In this case, let us try to see what are the different components, leakage current component that is flowing through it. Okay, so the first one is, let us take the first one. First one is the reverse bias PN junction. What is this reverse bias PN junction? Reverse bias PN junction is like, suppose if you see here, this terminal is the NMOS transistor, NMOS kind of devices. This is the PMOS kind of devices. Okay, so if the body terminal is at higher potential or something like that, and this is in the at the lower potential, or in opposite sense, like if the drain is at higher potential and the body is at lower potential, so N is connected, or the N type kind of semiconductor is connected to the higher side, and the P type of semiconductor material is connected to the lower side. Okay, so if this is low, like let us assume this is the NMOS transistor, right? So for the NMOS transistor, the body terminal is connected to the ground. We know that the body is connected to the ground. Because the body is grounded, and if I have applied some drain voltage, okay, so in that case, this junction which we have created over here, like between the drain to body and the source to body, that will create some reverse bias PN junction. Okay, and if they are creating some reverse bias PN junction, what it means, that will yeah, so that will some current will flow between this drain and body and the source and body. So this kind of current, we call it the reverse bias PN junction current. Okay, so let me represent in the proper color, because I have given the red color for this. So the current that will flow between this one and this one is the I1. Okay, so these are the I1 that will flow here. Okay, now let us talk about the second case. Okay, what is the second one? The second current component is the subthreshold leakage current component. What is this subthreshold leakage current component? Let us try to see. We know that if the device is in the off state, okay, if the device is in the off state, then what will happen? There should be no current flow between the drain and source, because there is no channel formation. But what happens if, like, we know that the device is turned on if the VGS is greater than the VTH. But suppose if I have applied some potential at the gate side, okay, which is less than VTH, so ideally the device should be in the off state. Okay, device should be in off state, but because I have provided some voltage at the gate side, some of the channel has been created over, even though that is not sufficient to flow the current, but some channel is created. Okay, some some of the minority charge carrier has been accumulated at this interface. Okay, so because of that, some minimum current that will start flowing between source and drain, even though the threshold voltage was less, like the VGS was less than the threshold voltage. Let me repeat it again. What happens? We know that to turn on this device, we have to make the VGS that should be greater than the VTH. Okay, but if I have increased this VGS, which is non-zero, if the VGS is non-zero, but less than VTH, okay, VGS is less than VTH, in that case what will happen? Ideally the device should be in the off state, but because the VGS is non-zero, some of the channel will be created at this one. So because of that, some current will flow, and that current we call it the subthreshold leakage current. Okay, subthreshold, why? Because the threshold voltage is, like, the VGS is lower than threshold voltage. That is why the current due to the subthreshold, we call it the subthreshold leakage current. So the subthreshold leakage current will flow between this one if the VGS is non-zero and less than 1. Yeah, let me write the proper. VTH is greater than VGS and VGS is non-zero. So this is the condition for subthreshold leakage current. Okay, so this is all about the subthreshold leakage current. Now let us talk about the third case. So basically there are 6 leakage current component that comes into the picture, especially at the skilled technology. Okay, so the first and second is the reverse bias and the subthreshold. So these two currents which we discussed in the previous slide, right? So the reverse bias PN junction diode, which is created between the drain and the body terminal and the source and body terminal. And the second one is the subthreshold leakage current. Okay, so this is what the meaning of these two things. Now what happens? The third kind of leakage current is the gate oxide leakage current. So gate oxide leakage current is due to the tunneling of electrons between gate and the substrate region with high electric field is applied at the gate oxide region. If high electric field is applied at the gate side, because we know that with the technology scaling down, the size of this oxide or the thickness of this oxide is very less. Okay, and if the thickness of this oxide is very less, in that case what will happen? There may be some electron that can tunnel between the gate and the substrate. Okay, so there may be some tunneling of current, electron or current, we can say the same thing. Okay, and because of the high electric field. Okay, because see, if we are scaling down this oxide and we are maintaining this gate voltage or other things, then the energy will get sufficient energy, right? So they will start tunneling through it. So because of that tunneling, there may be some current flow, and that current flow we call it the gate oxide leakage current flow. Okay, so the gate oxide leakage current is flowing between the gate and this one. So this is nothing but this is I3. Okay, so this is all about the I3. Fourth component that can happen in the devices, that is the gate current due to hot carrier injection. Okay, what is this gate current due to hot carrier injection? Hot carrier injection is that results due to the reduction of threshold voltage by electron volt trapped into the oxide layer. Okay, so what happens if the with the time, like the electrons or the charge carrier get the sufficient energy. Okay, they have the sufficient energy, kinetic energy, and because of the sufficient kinetic energy, because we have reduced this oxide. Okay, and we have reduced this oxide, and because of this reduction in the oxide and the high energy that the charged particle has gained, and because of that high kinetic energy, some of the charged particles they can trap into the oxide region. Okay, and if they are trapping into the oxide layer, so there may be some leakage current flow, that can flow some leakage current flow. Okay, so if they are trapping into this one, so like the fourth component we can say like the current flow because of this one, that so let me write in this way. So the I4 is the fourth component that we are calling it the hot carrier injection. Okay, so let me repeat it again. What is the hot carrier injection? Hot carrier injection is nothing but this is because of the reduced threshold voltage. If I have reduced the threshold voltage, so and the size is very small, so some of the charge carrier can get the sufficient energy, and because of that sufficient energy, they can start trapping into the oxide, and because of that trapping, some current can flow. So that current we are calling it the hot carrier, the gate current due to the hot carrier injection. So the I4 is that current. Now the fifth current, let us talk about the fifth current. What is that fifth current is? The fifth current is gate induced drain leakage. What is that gate induced drain leakage current? Okay, so the gate induced drain leakage current, if the large negative gate bias is applied, then the movement of magnetic charge carrier between the channel and the substrate region, there may be some. So if I have like if I have applied a large negative voltage, if the large negative bias is applied, then some of the magnetic charge carrier will start moving between the channel and the substrate region. And because of, so see, suppose here we have some channel, okay, and here we have some substrate. So because of that, might be some current can flow between the channel and the substrate. So we are calling it the gate induced drain leakage current. Okay, so the gate induced, let us assume I have some channel at this one. Okay, some channel is formed, so this current we are calling it I5, and that is the gate induced drain leakage current. Let me repeat it again. What is this gate induced drain leakage current? So the gate induced drain leakage current will flow if the large negative gate bias is applied. So if the gate voltage is largely negative, like it is zero, in that case some of the magnetic charge carrier from this channel, they can start flowing between channel to this bulk one, substrate one. So because of that, there may be current flow, and then we are calling it the gate induced drain leakage current. Okay, the sixth one, there is a last one, last leakage current component. That leakage current component, we are calling it the channel punch through current. Okay, what is that channel punch through current? The channel punch through current, punch through current is the current flowing between the source and drain region when channel disappears. Okay, so there may be some current flow between the source and drain without including the channel. Okay, if there is no channel, and still there may be some current flow, because the technology node is very small, so L will be very less, and if L is less, in that case might be there may be some current flow between the this one, source and drain one. Okay, and because of that, we are calling it the channel punch through current. Okay, and this current is the I6. So I'm giving 1 minute time to think about all these leakage current components. In case you have any doubt, please let me know, and I will explain it again. Okay, otherwise we can move ahead with the power dissipation. So we can think for 1 minute, and then we can move ahead with this one. In case you have any doubt in any of this component, then you can ask. Okay, so if there is no question, then we can move ahead with the leakage power. Okay, so see here, leakage power dissipation. Yes, so if we go into the more detail of this structure, like if you see the previous structure, we just saw the 6 short channel effects, starting from reverse bias PN junction, subthreshold leakage current, gate oxide, gate current due to hot carrier, gate induced drain leakage current, channel punch through current. So if we combine all these things, then the overall the power dissipation due to these components through the transistor, we call it the leakage power dissipation. The leakage power dissipation increases with the technology scaling down. Okay, so if I'm scaling down the technology, the leakage power dissipation increases. Okay, so if I want to write in more detail about these things, so if I'm talking about the IG, okay, so gate current, which I just told you, gate oxide leakage current. So the gate oxide leakage current can contribute in 3 directions. Either it can IG, gate to source can be there, gate to body could be there, gate to drain could be there. So if you break the gate oxide leakage current, then that could be there could be 3 component. One component could be IGS, second component could be IGB, and third component could be IGD. So these 3 can be the component for the gate oxide leakage current. Similarly, if you are talking about the this one, gate induced drain leakage, okay, so the gate induced drain leakage will be there, and there could be like gate induced source leakage can also be there. Okay, so the both kind of component we can observe, especially if I'm considering the gate induced one. Okay, because the channel is from here to here, so the gate induced we can observe from the source as well as from the drain side. Okay, so that is why this will be punch through. Yeah, this is we have already discussed. If we talk about the junction leakage current, which like the reverse bias PN junction, So the reverse bias PN junction can be for the drain side as well as for the source side as well. So these are the some detailed one. So this is not only the single component, we can observe the many components as well. So this is all about the leakage power component. If you go into the more detail of some components, like if I'm talking about IGS, like gate to source, IGS like the current which is flowing, gate oxide leakage current between the gate and source. So this could be like IGS 0 could be one of the component. Yeah, again this IGS can be break into the two part. One will be the IGS naught and the second one will be the IGCS. What is this IGS naught? IGS naught means if I'm considering only the overlapped portion, okay, in the overlap portion, not the channel, then that will become the IGS naught. And if I'm considering the gate to source including the channel, then that will become IGCS. Okay, so this will give you the overall IGS. So IGS can have the two components, that will be IGS naught plus IGCS. IGS naught indicates like from the overlap portion without including the channel, and IGCS that includes the channel. Okay, similarly IGB is the normal one that will flow, and similarly for the IGD you can break into the two part, IGD naught and IGCD, which includes the channel as well. So this is all about the different components. Yeah, so you can break all these components in a different way. You can have a more number of components. So this basically these components gives you the more insight or more detailed current component, especially the leakage current components. Okay, so based on the operation, based on the conditions of the channel, based on the potentials at different terminals, these kind of leakage current components can play a major role in the leakage power dissipation. Okay. So the leakage power dissipation can be like, if we summarize all these leakage current components, whatever the leakage current component we have, then after multiplying with the VDD, you can get the leakage power. Okay, so this is all about the leakage power, and that we can calculate from this one. Okay, so this is the leakage power. Now if
Sir,
yeah please.
sir, in previous slide, please go in previous slide, sir.
Yes, please. Yes.
Sir, I have question on I2, sir. It occurs.
I2s.
Yes.
Okay, let me explain it. Suppose we know that the device will be in the on state if the VG. Let me change the color. We know that if the VGS is greater than VTH, okay, this is the condition to turn on the device. This is the NMOS transistor, so this is the condition. Okay, now what happens if I have some VGS? Okay, if I have some VGS which is less than VTH, what it means? The device is in the off state, so there should be no current flow between the source and drain. Okay, but because the VGS is non-zero, there is some voltage that we have applied at the gate side, so some of the channel will start forming at this one. So channel will, like, even though the inversion layer will be created at this one, and if the inversion layer will start creating, it will get some minute path to that current can flow through that one. Okay, even though the channel is not that much sufficient to turn on this device or to perfectly flow the current, but because we have some non-zero VGS, because of this non-zero VGS, some inversion layer is there, some channel is there, minus channel is there, so through that channel some current can flow, and that current we are calling it the subthreshold leakage current. So the subthreshold leakage current is like, if the VGS is less than VTH, ideally it should be in off state, but because of the inversion layer some current will flow, and that current is the subthreshold. You got the answer?
Okay. Yes, sir. Below the VTH, the channel will form, na?
Channel will form, but not that much sufficient to flow a proper current between the source and drain. So
I2 will occur.
I2 will be there. Yes.
Below VTH.
I2 will be there if VGS is non-zero.
Okay.
If VGS is equal to 0, then the I2 will be 0. Okay, but
Yes.
I2 will be I2 will be there if the VGS is non-zero. Okay,
Yes, sir. Yes, sir. Yes, sir.
you got the
Okay,
answer
sir.
or no?
Yeah,
Fine.
got it, sir.
Fine. So this is all about the leakage current component. Yeah, this is the more detail, and we can calculate the leakage power with the help of I leakage and the VDD. Now let us try to summarize. Like as of now, we have studied the 4 different kind of the power dissipations. The first one is the dynamic power dissipation. Second one is the short circuit power dissipation. Third one is the static power dissipation, and the fourth one is the leakage power dissipation. So the total power dissipation through the circuit or any of the CMOS circuit, that could be like that like if we add all these components, then that will become the total power dissipation. Okay, so the total power dissipation, like, yeah, simply just putting the value of all these things, and then you can get the total power dissipation. So this is all about the total power dissipation that can dissipate through a CMOS circuit, any of the circuit. Okay, now the 2 parameters are left, then I need to finish it. Okay, so one parameter is the power delay product. What is this power delay product? As of now, we have calculated the 2 things, like the power we have calculated, like the different kind of power we just calculated, like dynamic power, static power, leakage power, short circuit power dissipation. So these all are the components which we have already calculated. Okay, now the power delay product becomes one of the important consideration, especially if I am talking about the like if I'm talking about the uh, how it could be, like suppose, see, as I told you, the threshold voltage is the parameter that decides what should be the power, that also decide what should be the delay, because we know that there is a trade-off between the delay and the power. So to analyze any of the circuit, only power is not sufficient. Like suppose you are designing some low power circuit, so you have to deal with the power dissipation. Suppose you are designing some high performance circuits, in that case you have to consider the delay, like delay should be as small as possible. But in the application, if you need both, like the power should be sufficient, like it should be as small as possible, as sufficient enough that we can tolerate, and the delay should also be not that much high. So in that case, one parameter comes into the picture, and that parameter we call it the power delay product. So the power delay product that gives the trade-off between the power and delay, and based on this product value or the power PDP value, you can analyze like if I have to consider the trade-off between the delay and the power. So what is the optimum the supply voltage at which we will get the minimum power delay product? So the minimum power delay product that will give you the optimum result. So let us try to see what does it means. Okay, so as I told you, the PDP is nothing but this is the multiplication of power into delay. Okay, if we talk about the delay of any simplified circuit, that is calculated with the, so let me write the delay expression. I have not taught about the delay, but let me write the expression for that one. Delay can be calculated as like delay or TP is the propagation delay, that is calculated with some alpha load capacitance, then some VDD divided by VDD minus VTH. Some other components are already also there, so let me write in more detail. VTX, okay, where the VTX is equal to the threshold voltage plus VD saturation divided by 2. Okay, so basically the delay of any CMOS circuit can be calculated with this formula. So yeah, I have not taken any lecture on this delay component, but yeah, for now just try to understand this is the delay component, where this alpha is the technology parameter and VT is the threshold voltage, VT saturation is the saturation like the drain voltage, saturation drain voltage. Yeah? VDD is the supply voltage, CL is the load capacitance. So this is the parameter that decides the delay one. Okay, so if we multiply the power and the delay, then you can calculate the PDP. Okay, basically let me elaborate more things. Like, yeah, let me change this color. So this portion is for the delay component. Now let us try to see here. Like we know that the PDP is the power into delay product. Okay, so so let me try to see. We know that the power is nothing but the that is given with the if I talk about the dynamic power dissipation, the power is given by FCCL square. What does it mean? It means that if I am increasing this delay, then power will also increase. Okay, so the graph for the power, that will look like this one. So if I'm increasing this voltage, then the power will look like this one. The power graph will be like this. Similarly, if we talk about the delay one, so delay is in the opposite trend. It is in the opposite trend. If we are reducing this delay, then this VDD, then delay will reduce. Okay, so the graph for this delay will look like this one. So this is for the delay. Okay, and if you multiply the power into delay, then you will get some optimum value. Okay, and that optimum value could be something like this one. Okay, so this is the power delay product. So the point at which we are getting the minimum PDP, that will give you the idea which supply voltage I have to use so that I can get the optimum power delay. Both the delay is not that much high, and the power is not that much high. So you can decide this optimum supply voltage. Okay, so let us try to write few things as well. Like if I want to calculate the power delay product for the dynamic logic circuits, like dynamic power I'm considering, in that case the PDP can be calculated as FCL VDD square, okay, into TP. Okay, if we talk about any circuit, CMOS circuits, and the maximum possible rate of frequency for any circuit, that could be like 1/2 TP. This is the maximum possible frequency that we can offer. Like what is the operating frequency of any circuit, that depends on what is the delay. Okay, so the maximum operating frequency that any circuit can offer, that is nothing that can be calculated with 1/2 TP. If the delay is very small, then the frequency can be very high, and vice versa. So the maximum frequency that we can have, that will be 1/2 TP. Okay, so similarly, if we try to simplify this expression, then this expression is coming out something like PDP, yeah, TP will be like 1/2 F max, and after substituting this one, I will get CL VDD square upon 2, and this is all about the power delay product. So the power delay product can be calculated by simply just multiplying delay and the power. Yeah, delay of any circuit can be calculated by this one, But the worst case or the maximum delay that any circuit can offer, that depends on what is the propagation delay. So if I try to put here the maximum F max, then the PDP will come out something like CLVDD square divided by 2. Okay, so this is one of the very important parameter, especially for the CMOS circuit, uh, to analyze the things. Okay, so this is what the power delay product is. The last component, I will take 2-3 more minutes, then I will finish this one. The last component could be like the energy delay product. Okay, so energy, like if like energy is basically like how much, if any circuit is charging and discharging, so it needs some energy to charge and discharge. Like suppose if I'm changing the input from 0 to 1 in any of the inverters, so the load capacitor will charge or discharge, so it requires some energy. So we also need, there is one more parameter that we call it the energy delay product. Okay, so energy delay product can also be calculated. But if we see the energy delay product, like energy can simply be calculated with the help of, like we know that the power is equal to energy divided by time. Okay, this is the simply E by T. Okay, what it means, if I multiply the power with the time period, then that will become the energy. And in the previous slide, if you go back, we have just multiplied the power and the delay is nothing but this is the time, maximum time, like minimum time that is needed to transfer the logic. So the PDP is nothing but PDP is the energy. Let me go back to this slide. If you see here, we know that the energy can simply be calculated with the power into the delay or power into time. Okay, so because we have already calculated PDP, so that is nothing but this is the energy. So energy during transition that we can calculate with the help of PDP. So the PDP is also known as energy. So this is also the energy. Okay, so now if I have to calculate the EDP and energy delay product, then what I have to do, I have to simply EDP is energy into delay. Okay, and energy is nothing but this is the PDP into delay. You can calculate something like this. Okay, and we know that the PDP we have already calculated. So PDP, if we have calculated like that is CL VDD square by 2, and if I multiply TP, then we will get the energy delay product. Okay, so this is what we can get it. So the energy delay product, like now this TP, just whatever the value we have just written in the previous slide for the TP, that you should use it. So it will be like CL VDD square by 2 into TP is nothing but this is the alpha times of CL VDD divided by VDD minus TX. TX, we know that what this TX is. Okay, so just by simplifying these things, I will get the EDP is equal to alpha CL square VDDQ divided by 2 VDD minus Vx. So this is all about the energy delay product. Okay. Now let us try to see. Suppose if we see here, if I'm increasing the VDD, in that case energy is going to increase. Okay, so if you see this part is nothing but this is the energy. Okay, so energy is the function of the VDD here. Okay, so the energy will increase if I am increasing the supply voltage. So this is the graph for the energy. Okay, now let us talk about what is the status of the delay. Okay, if you see this formula for the delay, that depends on the like if I this see this VDD minus VX. Okay, so the okay, sorry, VDD minus Vx, if I will reduce the VDD, then this component will become lower, more lower than the upper one. Okay, so the denominator will start dominating. So the delay component will be something like this. It will reduce like this. So this is all about the delay, which we have seen it. Okay, and similarly the energy delay product that can be calculated like this, EDP, and we need to find some optimum value on which we are getting the best supply voltage at which the EDP is maximum, so we can use it. So this is all about the energy delay product. So see, if you are analyzing any of the circuit, in that case you have to consider two things. First thing is power and second thing is energy. But at some supply voltages power could be less but the delay will be more, and the vice versa. So to find the optimum value, what should be the minimum supply voltage at which we can fulfill both the criteria for power as well as for the delay, then you have to come up with the power delay product. So the power delay product is needed for that purpose. Similarly, how much energy it can dissipate, like how much energy is needed to charge and discharge. To analyze that portion, we need to come up with the energy delay product. So this is how these two things are really important. Okay, so EDP and PDP, this is needed. So that's it from the power dissipation side.